Okay, so good afternoon, ladies and gentlemen. It's my pleasure to open this very special lecture. Very special because this lecture is co-organized with the city of Poznań and Poznań University of Technology. My name is Wojciech Sumelka, and I'm a Vice Rector for Science at the Poznań University of Technology. And it's my pleasure to represent here the Rector of the University, Professor Teofil Jesianowski. Today we have a very special guest, Professor Leszek Demkowicz from University of Texas at Austin. It's our great honor and it's our privilege, Professor, to welcome you to Poland, to Poznań University of Technology. And it is important to say, as you probably see from the name and the surname, that Professor is strongly connected with Poland. Of course, all details will be provided in the moment, but let me say that Professor originally graduated Jagiellonian University of Technology and also Krakow University of Technology. Now let me introduce Professor Mieczysław Kuczma, who will provide some details about career of Professor Demkowicz and about his scientific achievements. So, Professor, please.
Could I ask
Okay.
Professor Demkowicz also, because I just like to say a few words about. I mean, it is very great honor and privilege to me to introduce Professor Leszek Demkowicz. And Professor Leszek Demkowicz is a world-renowned scientist and civil engineer with outstanding scientific and organizational achievements. So he has contributed a lot to the development of science and also to the cooperation in the fields, especially in the fields of computational and engineering sciences. So as you can guess, it is a really difficult task for me to mention all the achievements and very rich records which are how I should say successes and achievements of Professor Leszek Demkowicz. So I would just like to mention a few of them. So born and educated in Poland, he has been working at the Oden Institute for Computational and Engineering Sciences, University of Texas at Austin, being affiliated with UT at Austin for more than 30 years now. Actually, he has started cooperation and research staying at Austin at UT even more, even earlier, I mean 40 years ago, and it was the time that I had the first contact with Professor Demkowicz then. And he has been working at the Oden Institute, which is one of the leading, I would say, scientific institutions in the world. And this institute, especially this institute, follows and actually confirms the motto of UT, which says, what starts here changes the world. And it is really so. So we will see this during the lecture, and this is the fruit, and this is the idea which is followed by the people working hard there. So at the University of Texas at Austin, Professor Demkowicz is assistant director of the Oden Institute, is holder of W.A. Tex Moncrief Junior Chair in Computational Engineering and Sciences II, is professor in the Department of Aerospace Engineering and Engineering Mechanics, and is professor in the Department of Mathematics. And as I said, born and educated in Poland, actually professor holds or has a Master of Science in Mathematics from, as was mentioned by by Rector Sumelka from Jagiellonian University in Krakow, and also Master of Science with honors and PhD and Doctor of Sciences degrees in mechanics, or actually civil engineering also, from Krakow University of Technology. But prior to joining the University of Texas faculty, he held various positions at the Krakow University of Technology. Just to mention a few, in the years 1991 till 1993, he was the head of section of applied mathematics and the director of computer center there. His work and scientific interests span across numerical analysis, adaptive finite element methods, and I remember the meeting and our talks. It was in the 1980s when the finite element method was already pretty well developed, but there were questions concerning accuracy and adaptivity, and the notion of hanging nodes will remain in my mind for the end of my days. It was really that concept which was resolved by the team of Professor Demkovic and Professor Oden there. And the other wide field of applications and actually effective solution problems were wave propagation, including acoustics, elastodynamics, and electromagnetics. Among the applications, Professor Demkovic and his group have developed original numerical methods for structural vibrations, analysis of acoustics. Let me just change the page. And the human ear, dynamic modeling of gears, analysis of the optical waveguides, calculation of radar cross-sections, both electromagnetic and acoustic. So this is a wide variety of problems which were treated and analyzed in depth by Professor and his team. And his research on high accuracy adaptive methods was summarized in a 2-volume book, Computing with HP Elements, which were published in 2006 and 2007. And for this work on HP methods, Professor Demkovic was awarded the Demkovic Medal by the Polish Association of Computational Mechanics and the Computational Sciences Award by United States Association for Computational Mechanics, both in 2009. And just now some, I would say, some headlines. Professor Demkovic has co-authored or co-authored 7 books. In particular, he authored a monograph on adaptive methods. It is written in Polish in 2006, and actually it is a habilitation thesis.
1996. 1986.
1986, so excuse me. And co-authored with Professor Tinsley Oden a famous book, Applied Functional Analysis, which that version of issue was published in 2016. Professor Demkovic is the co-author of over 200 journal articles and other publications in the general area of computational mechanics and mathematics. He was the editor-in-chief of the Elsevier Journal Computers and Mathematics with Application in the years 2012 and 2017, and serves on editorial boards of 10 international journals. He's a founding member of the Polish Association for Computational Mechanics and its first president. It was in 1991, and he was president for 2 years, and now is a honorary member of this Polish society. And in the years 2016, 2018, he served as president of the United States Association for Computational Mechanics, and he's a fellow of both US and International Association for Computational Mechanics, and member of many other scientific international organizations. In 2000, and this is the topic actually which will be discussed, the last fruits. In 2009, Professor Demkovic co-invented with J. Gopalakrishnan from Portland University the DPG method, discontinuous Petrov-Galerkin method, with optimal test functions, which has been the focus of his research for the last 13 years. And yes, and for these achievements, he was awarded the ICM Computational Mechanics Award. And these are just facts which characterize or summarize in some sense the achievements and professional activity of Professor Demkowicz. But finally, I just like to add some sentences which are not of less importance. Professor Demkowicz is a very kind person, and I had the possibility to visit, I mean, him and his family, and I can say that Professor Demkowicz as a scientist, but also together with his wife Stasia, they are the very good ambassadors of Poland and Polish culture and Polish tradition abroad, not only in the US, but also in other places when they are, and they activity and for other people is really very high. So I am really very proud that I can know and can be in contact with such a person, such a personality. So thank you very much that you accepted our invitation to visit Poznań, and we are looking forward to your lecture. Thank you very much.
Thank you. Thank you. I think I'm wired. So,
Okay.
so it's my honor and pleasure to be here in Poznań, and I'm very thankful to the city of Poznań and the Poznań University of Technology, in persons of Rector Sumelka and the old friend Mietek, to be here to deliver this lecture. You didn't mention that this is 31st anniversary since we had organized a similar short course shortly after the establishment of Polish Association for Computational Mechanics. Tomek Wodegowski, another big friend from here, was involved in that. That was 31 years ago, right? And I remember then came up with an ingenious financial solution to the problems that the Polish Association was encountering. We just didn't have money. People didn't want to have money. And I think it was Tomek that suggested, you know what, we will pay you for the short course, and if you're kind enough, you donate the money to the association and pay for all the members membership. And that indeed has solved the financial problem of PSA, CM, KKM for the first 3 years or so, right? It's really a pleasure to be in the great city of Poznań, one of the most beautiful cities in Poland, and amongst friends and such wonderful people. So, having said that, I was told that I have a full hour. Mietek took 15 minutes of it, right? So be prepared to suffer for about 55 minutes to a full hour. This is a lecture that I'm actually delivering for the third time. It's supposed to be, is directed at technical audience, but not necessarily mathematicians. And it reflects two things. It reflects the history of numerical methods, discretizations, in particular finite element method, but it also reflects my personal career, the subject, because as you will see, I have been growing with the subject throughout my whole career, starting, you know, at civil engineering department, where you start with statics problems, then you go into dynamics, wave propagation, and as you expand your horizons, you have to also expand your mathematical tools. So, no presentation on the subject can start without mentioning my mentor, friend, for now 42 years, Professor John Tinsley Auden, who whose institute, the institute that he established, is named now after him in 2019. The story started in 1974 with the establishment of the famous TICOM Institute. Many other institutes worldwide were named mimicking that abbreviation. There is a BICOM, right? Then Mietek was a guest for several years at Brunel University. There's RICOM here in the neighboring Linz, and so on. in '93, when I moved permanently to Texas to help building a new institute and new program, we were looking for a name that would differ only incrementally from TICOM, not to lose that tradition. And we came up with the acronym called TICAM. Many people didn't even notice that the acronym had changed, but the meaning, as you can see, was quite different. We went from mechanics to mathematics. And the biggest organizational change at that point was that this was no longer a small departmental institute involving 6 or 7 professors, but it became a university-wide interdisciplinary institute under auspices of about 4 different colleges and involving professors from many, many different departments. In 2003, we underwent a huge expansion, and the name was changed following the request of our great donor and benefactor, Peter O'Donnell. He died last year. The request was, okay, shouldn't be anymore something local related to Texas. I want that to be more national, international. And the name was changed to the Institute for Computational Engineering and Science. Professor Oden is responsible for coining the term computational mechanics at the beginning of his career, and he was one of the first few people who began to use that phrase, computational engineering and sciences. Right? ISIS was established in 2003, and now is shortly Oden Institute, like Courant Institute. So we discussed the grammar behind that just before lecture. We say, I work at Oden. Dr. Oden is still working at 85, and his email address is oden@oden. Okay. So that's the very quick scope of my presentation. I'm going to spend a couple of minutes for a general audience introducing the subject of computational engineering and sciences, and then we'll say a few words about how we educate our graduates in this subject. You know, if I could point to my personal accomplishments, then I would say my biggest accomplishment is to work with young people, and having graduated a number of PhD students, master students, and so on. And these people that take what I have been teaching them to my entire life, then to the real world, is my real pride and satisfaction. So I will give you some examples. And then the last 50 minutes is going to be a crash course on this very mathematical subject, very fundamental subject, which in fact summarizes a class that they teach. And the class is 1 semester, so you're going to see 1 semester class abbreviated to 50 minutes, okay? So the computational engineering sciences lie at the intersection of 3 fields. Analysis, that means heavy mathematics. It's not the applied mathematics or typical engineering mathematics, it's much heavier mathematics. Modeling, this is where engineering comes as a subject, but it also could be science, could be finance, right? Could be geomechanics. And then computing. You have to know a little bit about the computers, software engineering, and development of non-trivial programs. And the students that we educate have to become specialists in all 3 subjects. So this itself already says that the program is difficult. You really have to excel in subjects that, in principle, you could get a PhD in each of those 3 individual subjects. This is a typical modeling paradigm. We start with a problem to solve. Could be an engineering or science problem. And then we have to model it first. And that modeling part is more or less translation into a system of partial differential equations. And once we establish that system of partial differential equations with proper boundary, initial conditions, so on, there comes analysis. Right? This is where the math part is very heavy. Now, once you have established that, you discretize the problem and you create a discrete model. And this discrete model is the subject of numerical analysis, which in particular also is involved in investigating the relation between the 2, the convergence process. And then finally, the discrete model is translated to computer code. This is where the software engineering comes into the picture. And once you got computer results, you have to be able to interpret them, so back to physics to understand the solution. There are 3 important processes in this, verification processes in this paradigm. The code verification, you have to make sure that your code is bug-free. Then verification, where you verify your discretization. And validation, where you make experiments, do experiments to to verify the actual modeling of the problem. Of course, machine learning, that I believe is a hot subject here as everywhere else, has disturbed a little bit this paradigm and is present in every place of this paradigm as well, starting with the modeling. Many of my machine learning colleagues claim that this whole paradigm is over and the machine learning takes over. I don't think this will happen. Machine learning is a great tool, but it's just a tool, and it will quickly find its place in this paradigm as well. So this is how our program is built. I indicated 3 areas. In all those 3 areas, we call them applicable mathematics, scientific computations, and modeling, areas A, B, and C. Students have to take 4 classes, minimum in each, and the classes in red are obligatory in the first year, after which they have a qualifying exam. And then if they come with little or no experience in coding, they have to take supplementary software courses, learning simply advanced languages. So to give you examples, I'm going to make it very personal. These are my last 3 PhD graduates. Socrates Petrides came from Crete. He was a very special case because he came over 10 years ago as a fellow of a Fulbright fellowship and came just for master degrees. And he approached me in the spring and said, "Oh, I miss your class on function analysis. Could I still take it with you as individual instructions?" And he did. He was a fantastic student. And by the end of the semester, I was so impressed with him. I said, "Socrates, you take the qualifying exams, right?" And he says, "I'm not staying here for PhD." I said, "Well, you're staying or not, take your qualifying exams, because I'm sure you will pass them and you will have a window open to come back if this turns out to be the case." So I convinced him. He passed it with flying colors, left, got married, served for 3 years in Cyprus, military, and after 3 years things did not work out exactly the way anticipated. He came back. By the time he contacted by email, I forgot who he was actually. But I had to keep my promise. I took him back, found out money to support him. Wasn't that easy because not a US citizen. As you can see, he took a tremendous number of classes and turned out to be one of the best students I have ever had. I didn't write it here. For his PhD dissertation, he got the annual Best Dissertation Award in the Institute, a big, big distinction. And he is now a full staff member at Livermore National Labs in their computational applied scientific computing group. Very high position, very well established already. Second graduate is from Colombia, an engineer, pure engineer, who came and studied mathematics. You can see this large number of classes. He graduated during COVID in November of 1920. And because he was a Fulbright fellowship, he also was forced back to go to his native country. And there now he holds a assistant professorship. And finally, the last student who is now a postdoc at the institute. And if I could make it very personal, I would say this is the best student I have ever had. He is really more like a son to me than a student. Stefan Hannekin from Germany came with a very advanced and appropriate degree from University of Erlangen, then got his master at Georgia and joined us in 2018, and shortly after arriving Austin joined my group. He developed a parallel version of the code that I've been working on. It was the subject of the short course that we taught here 30 years ago already, at least it's first or second version. And as you can see, he also took a number of large classes. Okay, this is the first job after graduation. As you can see, most of the students stay as postdocs around. The number now in government labs, this is 4 years old. Government labs is much larger, about 15%, and the industry is also large. Okay, so that was an introduction, and now I go into the subject of discrete stability. So this is the famous phrase that I start every class on finite elements with, and the class says that that phrase says that stability and approximability imply convergence. And it corresponds to this fundamental estimate where the approximation error, the difference between exact and the approximate, say, finite element solution is bounded by a constant known as the stability constant times the best error in measuring the same norm and using the trial space that you can get. It's called the best approximation error. So the question is how to formulate the problem, what norm to use, what is the energy setting, do we have this stability, how to guarantee the stability, and how to guarantee this fundamental paradigm. And I will take you through the mathematics of it and the history of that in a few words. So the whole story starts with the variational formulation. And I know this is scary for non-mathematicians, but this is the language that we use in the final method, or Galerkin method. Language of two spaces, energy spaces. These are Hilbert spaces, trial space and a test space. A bilinear form that represents equations, a relaxed form of the equations, and material data, and a linear form that represents a load. And the point is that every boundary value problem, initial value problem, can be cast in this abstract form. I should have said every linear problem. I will talk about linear problems only today. So what is confusing is for non-mathematicians that the same problem can be cast into this variational formulation in more than one way. In fact, in many ways, right? That's the big difference between mechanical engineering and computational math programs. In mechanical engineering, you're learning the variational formulation, doubled as the principle of virtual work, and that's the only one you begin and end your education with, right? One of the big points in computational engineering math is that the same problem can be formulated using many different variational formulations. They differ in the energy setting, then they differ in kind of norm in which you converge, and depending upon the application, one may be better over another, right? I will be talking about those things starting tomorrow morning already. So that's a comment. Now, if you take this bilinear form and you can rephrase it as an operator equation, but the key point is that the operator that you introduce corresponding to this bilinear form takes values not in the test space, but in the dual space to the test space. So we might argue that the very nature of variational formulations is dealing with operators that go from one Hilbert space into the dual on another space. Why am I making this connection? Because this is where we connect with the greatest Polish mathematician, Stefan Banach. In this very year, we celebrate 100th anniversary of his PhD thesis, right? And Banach worked on linear problems represented with the operator B, except that he worked from X to Y, right? So the peculiarity of variational formulation is that your Y becomes the dual B prime. You have to conquer the concept of the dual space. And one of the most famous theorems proved by Stefan Banach is called the closed-range theorem, says roughly that this problem is well posed even only if the operator is bounded below. Bounded below, so if you look at the value of B on U and measure it in the proper dual norm, then this is bounding below the norm of the solution times some boundness below constant, right? Closed-range theorem. This is what we teach actually in the second year for engineering students with engineering background and first year of students with math background. Stefan Banach, big connection. Now you might say, what's the big deal if we have the Banach theory? Well, okay, so first of all, a closer look at the boundness below. This is this condition. If you just rewrite it in, right-hand side going to left and divide by gamma, then what you see is the boundness below is simply equivalent to stability. Right? The solution U is controlled by a constant times the value of the right-hand side. Right? So the problem, part of the well-posedness definition by famous French mathematician Adamard, includes the conditional stability. So it turns out that the stability condition translates into boundness below condition is not only necessary, but it's also sufficient for the existence. The people that establish that connection with the Banach theory, okay, there's another connection. You're looking here at the dual space, and if you recall the norm in the dual space defined to the supremum, and then divide by this, you end up with the observation that boundness below, in context of variational formulation, is equivalent to the famous in-sup condition. And the moment I have said the words in-sup condition, Professor Babushka comes in, my colleague for 30 years, and one of the most famous applied mathematicians ever, founder of mathematical theory of finite elements, Czech, from Prague. One of the asteroids is named after his name. There's a Babushka asteroid. Prolific author, about 500 or so papers, huge number of citations, and a creator and initiator of many, many, many fundamental concepts in finite elements and in theory of finite elements. Too many for me to mention here, even in a few minutes. The Babushka Nečas theorem, and Nečas was the very first graduate student of Professor Babushka. Professor Babushka is still alive. We just celebrated his 96th birthday. Professor Nečas, unfortunately, died of cancer in 2002. They established that the in-sup condition essentially implies well-posedness, uniqueness, existence, uniqueness, stability of variational formulations. And what I try to communicate to you is that that result is in direct connection and relation with the Banach closed-range theorem, right? So, but everything is easy once you know it, right? They were the first one to notice this connection. Okay. Now, once we have established that we have a well-posed problem, we discretize it. And this discretizations in this context bear the name of the famous Russian mathematician, Boris Galerkin. There are a lot of anecdotes about him. He published his very famous paper about what we call now Galerkin method in 1914. So he just took that variational formulation that we look at and said, first of all, he worked only with the symmetric case, where the trial and the vector space is the same. And he said, okay, we're going to replace V with a finite dimensional subspace. And in both where we look for the solution we test from. And then this will be worth a solution of the linear system of equations, as you will see in a moment. There are a lot of anecdotes about Boris Galerkin. Of course, being a famous professor, by the end of his life, he also had a high position in the military. He was a colonel. And if you read the web page, beneath the web pages, they were built, you know, with the information about him. Apparently, every time soldiers during World War were saluting to him, he would cover his face because he was scared to death. And then it meant something different. He was not a very military person. Okay. A few years later, 20 years later, another version of the Galerkin method popped out, and that's the Petrov-Galerkin, or Pietrov. Georgy Pietrov was a Russian aerospace engineer, and obviously he was dealing with problems with huge convection. They're non-symmetric, and he generalized the Galerkin method by assuming that the trial and the test spaces may be different. But of course, by the time you discretize, these approximate two spaces must have the same dimension. To distinguish between Pietrov-Galerkin and Galerkin method, we very often assign the name Bubnov-Galerkin to the original method. Bubnov was a colleague, friend, and collaborator of Galerkin in the Institute of Hydrodynamics at then St. Petersburg University, later Leningrad University. Okay, so if you take this UH represented in terms of basis functions, and you do the same test for the test functions, plug it into this formulation, then you use the linearity of B and L, and you end up with a system of linear equations, where on the left-hand side you see a stiffness matrix, and on the right-hand side you see a load vector. So this approximate problem is simply worth solving a system of n equations with n unknowns. And now the big question is, you know, how do we guarantee that this system, this discrete solution, has anything to do with the exact solution? And I will start here with the famous Babushka theorem from 1971, that it's not the first theoretical result, historically established on the subject, but it's the most illuminating one, and it corresponds exactly to the in-soup condition that we talk about. If you satisfy a discrete version of the in-soup condition, and watch out, that was equivalent to boundness below in Banach, but now it's on the discrete level, then you also have existing uniqueness and discrete stability of the approximate solution. So there's nothing new here, because this is the same Banach theorem, Lagrange theorem at work. However, the new thing here is that this discrete in-soup condition implies also convergence. The error is bounded by the best approximation error times this ratio of continuity constant for the bilinear form and that in-soup constant gamma h. So as long gamma h is bounded away from 0, then we have this term here, uniform discrete stability or shortly discrete stability and approximability imply convergence. And when I start a class on mathematics of finite elements, I make my students to recite this sentence for about 5 minutes, because I tell them, if you forget everything that I teach you, please remember this phrase. It's so fundamental. You want your method to converge, you have to establish these two things: discrete stability and approximability. So you have to be sure that with the functions you're using to approximate solutions with, you can approximate the exact solution, but also you have to make sure that you have a stable solution, because otherwise you will not converge, right? Ivo wasn't the first one that coined that phrase. That phrase actually was coined about 6 years earlier in context of finite difference methods by another great American mathematician, Peter Lax. He came from Hungary during World War II and started his career at Courant Institute, and it's still there, and he's exactly the age of Ivo, 96, still alive. So if nothing else, discrete stability gives you longevity in the long run. You have a long and very established life. And of course, but in both questions is, how do we assure this discrete stability? And this is where I'm going to take you now to the historical journey of how this discrete stability was guaranteed and established by different people in different times. So the story starts with Rietz. Walter Rietz, a young German physicist, right, investigated the variational problem under the additional assumption that this bilinear form is Hermitian or symmetric. And under this additional assumption and positive definite, he established that the variational formulation is equivalent to the minimization of the energy. So if you are a student in civil engineering department, this is half of your courses. Lagrange Theorem, right? When I was a student, I was told the Lagrange Theorem in context of linear elasticity, then for beams, then for plates, then for shells. And then finally it struck me, they're talking about the same thing. And the proof of that is actually 2 lines or 3 lines. So this is the power of mathematics, very concise and precise way of pinpointing the main ideas, right? But it is less known that, of course, the same thing holds for the discrete problem, but it's less known that this condition is equivalent to the condition that the approximate solution actually minimizes the distance to the exact solution in the so-called energy norm. The energy norm is defined by the bilinear form. So if you have the Rietz scenario, which, as I said, is the case for most of the static civil engineering problems, you establish the best approximation error, right, in the energy norm. And how that gives you stability? Well, you introduce the concept of V-coercivity, which establishes now equivalence between the energy norm and the actual norm, and along with the continuity estimate, you're getting this stability estimate, and as you can see, the stability constant is simply square root of m over alpha. So as an engineer, if you want to say whether your problem is or is not stable, how much it is stable, you have to start paying attention to these two constants, continuity and cursivity, and develop your mathematical engineering intuition of how they depend upon the material data, how they depend upon the shape of the domain, and so on. However, if you are okay with the energy norm, you have a perfect method with constant 1. Your method delivers the best approximation error. Okay, so that was the end of 19th century, way before Galerkin actually, right? This is an a posteriori interpretation. And then for a number of years, there was no math on the subject until Professor Solomon Mclean appeared on the scene. A big name in applied mathematics. He suffered a lot from communists. He was not allowed to leave the country, never. He had great friends worldwide. In '89, when Russia opened up for a short period of time at least, he was visited by great Italian mathematician colleague, Professor Ficera. Many of you know the name of Professor Ficera, with variation inequalities, right? Many other subjects. And he came to his apartment in a large building complex of apartments, essentially at the moment when Professor Mclean was dying. He was present at his deathbed. Very sad story. Never could enjoy even one day of freedom. Professor Mclean is responsible in context of Galerkin method for what we call asymptotic stability argument. He investigated the case when the bilinear form is this Hermitian and positive guy, think in terms of strain energy, augmented with a compact perturbation. So the compact perturbation may have a plus or minus sign, and the best example of compact perturbation is the mass term. So physically speaking, when you move from Ritz to Mclean, you move from statics to dynamics. You are able now to analyze vibrations. And this was exactly what happened to me when I started to study acoustics of submarines at the end of '80s, beginning of '90s, and overnight I had to learn the Mclean theory and expand my horizons. So what that theory says that under these assumptions, only when the mesh is fine enough, you can satisfy the discrete in-sub condition. And actually, I managed to prove extra things. The approximate in-sub constant converges to the exact ones, and the ratio of the, if you measure the energy of the best approximation error and the actual error asymptotically converges also to 1. I published a number of papers on the subject. How does it work in practice? This is a baby problem, vibrations of an elastic bar with a number of either 5 wavelengths or 25 wavelengths, and I'm displaying here 2 curves. The lower one is the best approximation error, and the upper one is the actual final approximation error that you get from the Galerkin method. And as you can see, there's a gap in between them. This gap was named after Professor Babushka and Frank Gillenburg, his former postdoc and now retired professor in Germany, as a pollution. This zero, the term is polluting the leading term. And as you can see, as the wave number increases, this pollution becomes bigger. And if you, after, let's say, 5% error, right, then you never work in this nice asymptotic regime where the 2 errors are identical. So solution is meaningless if you're in the pre-asymptotic regime. This is where the exact solution is, for instance, this wave. And if you just put too few elements in there, you're getting something that does not even remotely resemble the exact solution. And the convergence process is essentially nothing. And only once you had this asymptotic regime, you begin to see the convergence. These pictures are from my books that Mietek mentioned. You're welcome to read them and learn a little bit more about this. So Mclean, Ritz Mclean, 2 names to remember, right? After, of course, Galerkin and Piotr Galerkin. The third name that comes into the picture is French Professor Jean Serre. Jean Serre in 1964 published his dissertation and came up with what we call now the Serre's lemma. He established that more important than symmetry is the condition of coercivity. And if you satisfy the coercivity, then this automatically implies in subcondition, and then you're getting the same stability estimate with the stability constant m over alpha. So that was 64. I was a student, began as 71, and by 75 I started to work on my PhD dissertation, and Professor Gvidon Scheffer, my PhD supervisor, many of you know here, asked me to go to the library and pick up the dissertation of Jean Serre and prepare it for a seminar. And I came back from the library. This was 120 pages, not a joke. And I say, but professor, this is all in French. I say, what's a what? He says, you have dictionaries. There was time, there were no Google translator, right? So I had to sit down for about 6 weeks with a dictionary and pick up some French, which in mathematics, fortunately, is not so bad, and translate it to give the seminar and learn. A great experience in my life, right? Jean Serre and the coercivity. Now, this is what we were teaching in 80s and 90s. So I would say until I began to work on vibration problems, wave propagation problems, the word started and ended up with coercivity in my mind, right? Everything was about coercive problems. But then you start looking at things like convection diffusion problem. Here's that simple example, 1D. This is the energy, and this is the convection term. And if you, this is the proof of coercivity, but the coercivity, as you can see here, constant depends upon epsilon. So if diffusion is small, the stability constant becomes small, because for the standard Galerkin method and this type of problems, coercivity comes from diffusion, and that is not good enough. If diffusion is small, how does it manifest itself? Okay, here's a simple baby problem to solve, and if you have large diffusion, only 1/10, then approximate exact solution look very similar. But by the time you hit 10 to the power minus 2, you see there's huge oscillations, right? And technically speaking, the solution is stable, but with a very bad constant. So mathematically, there's a concept of uniform stability and robustness that we teach when you build methods where stability constant is supposed to be independent of epsilon. This is 10 to the power minus 3. Okay. So after we are done with, I'm going pretty fast. I may be able to finish in 10 minutes. I don't know. So after we are done with Serre, so let's try to remember the names. Walter Reeds, right? Galerkin, and Pietro Galerkin later. Mclean, Solomon Mclean. Serre, Jean Serre, and of course Professor Babushka and Professor Nechos. So those are the names to remember. The next big name is of Professor Franco Brazzi, Italian, who retired a few years ago, generated one of the best PhD students ever, among others Annalisa Buffa, Giancarlo Sangalli, Daniele Boffi, and others, very well established applied mathematicians these days. Franco studied mixed formulation, and the mixed formulation, you arrive at a mixed formulation, is a slightly different variation of formulation, right? By studying still minimization problems, but constrained minimization problems that you treat with the Lagrangian. So you add the constraint to the energy and you formulate the Lagrangian, and then you arrive at the saddle point problem. And he established a theory where you have not one but two in subconditions. So there's a number of anecdotes I can tell you about Franco Brazzi. You have a few some time. So Franco is my very good friend, and he said that he missed the deadline for applying to the Mecca of numerical analysis at that time. The year was 1970, Paris. This is where Professor Sierlet, Professor Raviard were leading a famous graduate program on finite elements, mathematics of finite elements. Professor Ravier was in charge. He arrived there, and Ravier says, "Oh, I'm sorry, young man, but we're done for this year with recruitment. We cannot take you anymore." And Franco started to cry. He came all the way from Pavia and wanted to be Okay. So this was on Friday afternoon. Say, "I'll give you a problem this weekend. Show me what you can do for Monday." And he gave him this problem. And on Monday, he practically came with a solution. That, theorem and theory, they made him famous for the rest of his life. So you can do a lot about stress, under stress, right? And that's one of the reasons why I never wish we should get away with the qualifying exams, written exams, and so on. There are many other famous examples like this. Start winning. Yes, absolutely. This was the case with Poincaré, Henry Poincaré, right? The greatest mathematician at the turn of the century. Poincaré and Hilbert were two big names by then. When Poincaré took his qualifying exam, he came out completely broke and said, "I solved only 2 out of 5 problems they gave me." But he didn't know that they gave him 5 open problems. Yeah, Hamilton is another case like this. He also managed to prove something. I don't remember exactly. No, with Banach's story was different. With Banach, the biggest story is about, him being discovered by Steinhaus. Steinhaus is the connection with Hilbert, because Steinhaus was 40-something PhD student of Hilbert, and he was by then established professor in Krakow. And he walked on Planty one day and overheard 2 young men talking about Lebesgue integral. The year was 1920, so it was 20 years after Lebesgue integral was introduced by Henry Lebesgue. So things didn't travel that fast as in the era of web pages and computers. So it took 20 years, to get this information from Paris to Krakow. Now, the peculiarity and the wonderful thing about the story is that both Banach and Nicodem was the second day, the famous Nicodem theorem, were both students of in high school of mathematics. They were high school teachers. Can you believe it? I mean, find me a high school teacher of mathematics that know what the Lebesgue measure and theory is about these days. This was the level of math high school teachers then. And so he overheard him speaking about Lebesgue integral and started conversation and presented Banach with an open problem that he didn't know how to solve. Next day, Banach came with a solution. That's how it started. Anyway, Franco is a great man, great colleague of me, and his theory is now the famous Insup condition. It's called the Babushka-Bretzi condition. Sometimes we call it Ladezhainskaya Babushka-Bretzi condition after the great Soviet mathematician Ladezhainskaya. And after a few years, Franco started to go around and say there's no double B condition, there's a single B condition. So people got offended, say, okay, Franco got crazy as he's aging. But what he meant was that there's, in place of Babushka and Bretz, is Banach. Because he clearly saw the connection, that's what I'm emphasizing these days, between the Banach's work and then the later work of Ivo. Okay, another big name, Tom Hughes, my colleague from the Institute. He's still active. Just gave one of the plenary lectures in Oslo at the ICOMAS meeting. The creator of SUPG, Streamline Abin Petrov Galerkin method, and the creator of the concept of stabilization. That was a great conceptual breakthrough. He says you can modify the left and the right hand side in the discrete problem with extra terms as long as you don't lose consistency. And if you are clever, you can do this modification in such a way that you can now gain discrete stability, right? Now the question, of course, is how do you construct those terms? And the answer is, well, you really construct those terms by looking at the residual. So these extra terms add typically all type of least square residuals and so on. And shamelessly, I will now advertised the discontinuous pattern Galerkin method that I co-invented with in 2009 with Jay, because that methodology offers a very general solution to the discrete stability problem. It guarantees that the discrete stability, once you have continuous stability with the use or construction of the use of very special shape functions, we call them optimal test functions. So you want to learn about that, I strongly invite you to the course that I'm beginning to teach tomorrow with Stefan. The course is going to be 6 lectures, 6 two-hour lectures. It's going to be very compact and oriented towards coding. Those are the subjects that I typically teach for a semester or longer, so it's almost impossible to condense it to a few hours. But we'll focus on the practical side of it and introduce you to a code that we are about to disseminate to the public. It's a huge code with which you can solve with order variable order p up to 9 problems up to 2 billion degrees of freedom. API open MP code, and the code that supports, in particular, the DPG method, and that's what the whole thing will be focused on. I think I talked too fast, right? Because that's the end. Thank you very much for your attention.
Thank you very much, Professor. I forgot to mention that after this short introduction, but Professor Kuchma, you have 1 extra hour. So yeah, but yes, now the presentation is open for discussion.
I have about 100 backup slides, if you already see us.
So now it's time for discussion.
Okay, I hope you remember the names. Banach, Reitz, Galerkin, Mclean, Babushka, Serre, Bratzi, Hughes.
Yes, but please use
the question. I mean, I'm just wondering, because after your presentation, you recalled many names, and the question I have just in mind, I mean, this is a little bit philosophical one, but I just like to ask: is mathematics discovered or created? How would you evaluate this process? Because one of the scientists and the other, they just approach and maybe better tune the model. Also, the question is mathematics a language just, or maybe it really discovers and reflects reality, physical aspects of the problem?
Okay.
If you
sure.
could
So if I can tell you what I think the honest answer is both, right? Because when you establish mathematical foundations of every theory, you have to start with honest axiomatic theory and making assumptions. And those assumptions are, of course, based on physics, on the understanding of the whole mathematical foundation and so on. Now, once you have made those assumptions, then the rest is discovery, right? For Banach, the biggest assumption was the finding the importance of the assumption of completeness of a vector space, right? Complete vector space that is named after all these years now after him and has the name of the Banach space, right? But once he made that assumption that he's dealing with a complete vector space, complete vector spaces, all the fantastic theorems that are at the heart of function analysis, closed range theorem, closed graph theorem, Hahn-Banach theorem, right? All of them are discoveries. And some of them, if you, for instance, care to read ever the proof of open map Banach theorem, it's very unintuitive. To this day, after having taught the subject for over 30 years, I have trouble, understanding where the hell he came up with the intuition behind the proof. Other proofs are perhaps more intuitive, but not this one. So the answer to your question, I think, is both, right? You write mathematics, you create in the beginning, but once you establish, then you begin to investigate the model, mathematical model, and this is where you discover things. And this is where a lot of faith comes into the picture, right? It's always a religious subject, because you have to believe that the theory that you are trying to establish makes sense. So intuition, connection with physics, right? All of this matters big way. Big way. So, you know, the students ask me, how do you know what subject to give for a PhD in a subject like this? And I always answer, you know, it's an educated faith. I start a new subject, I more or less have an idea how those things, but in the end of the day, it's a risk, right? I believe this can be proved, or this can be translated to a successful method because of this and that. But I don't have all the strings in my hand. If I had, this wouldn't be a PhD dissertation. There's a risk factor, right? You agree, guys? Same story.
Thank you very much. Next question.
May I sit? Okay. First of all, Leszek, I would like to thank you very much for your instructive lecture, because it was a kind of presentation which is really inspiring for the audience. Not only teaching everything, but inspires, what is very important. Thank you very much. As I understand, of course, you were restricted here to the linear problems. Yeah. Of course, we are engineers, so sometimes, unfortunately, we have to struggle with problems which are unfortunately non-linear, sometimes even not stable. And to which extent this mathematical thing should be extended, or what kind of difficulty you can see on the horizon, just to overcome them and really have the proofs, because in many cases we need really the proof that the solution which we are able to obtain in computations are really close to those which we don't know, and of course which are stable, and the solutions are really converged to the real solution which are unknown.
Right. So the answer, unfortunately, is contrary to the linear problems theory, that is, as I try to communicate here, founded on the fundamental work of Banach. There is no general theory for nonlinear problems. In principle, every nonlinear problem is a new field, a new challenge. Now, there are a couple of things I wanted to say. First of all, there are classes of nonlinear problems that bear some resemblance, and have some common foundations, and you perfectly know those. For instance, variation inequalities, right? There's a unified theory for variation inequalities. There's a unified theory for conservation laws, right? So a lot of CFD problems entertains, common theory, but even in there you have different splits. You have Friedrich's, theory. You have other theories. But at least there are classes of problems for which a unified theory exists, right? Most of the time, however, when we tackle a new problem in mechanics, introduce new constitutive equations, right? And now very often go from local to non-local mechanics, the famous example of peridynamics that is exploding now in terms of number of citations and work, right? The truth is, every new problem is a new theory. And a nonlinear problem is not well defined, that's my philosophical take on it, unless you give me precisely the linearization procedure, the path to the solution. So for a non-linear structural or analysis problem, this probably will be incremental loading, right? You load, or for post-backlink analysis, there will be the special path to avoid singularities, right? For CFD problems, this is going to be, even for steady-state problems, pseudo-time stepping, because these problems are stable in the space-time domain, but not in the space domain only, right? So if you tell me, okay, I want to analyze a nonlinear problem, I will immediately ask you, with what path to the solution? With what linearization path? because dependent upon the linearization problem, the same nonlinear problem may look completely different. Maybe a completely different new story. So we have foundations, a lot of fantastic foundations for nonlinear problems, but again, there's no general theory, and never will be. It's simply impossible. Right? It's amazing that Banach theory applies to every linear problem. Every. So you know, whether you're solving a system of PDEs or integral equations or integral differential equation, whether it's transient or whether it's as long as it is linear, the Banach theory on very general umbrella that covers that. But the moment you step out of the linear theory, essentially you're on your own. And then unless you fall into those well-established classes, you really have to start from scratch, which happens a lot of times. For instance, you know, as I mentioned, the peridynamics enjoys a lot of mathematical work the last decade or so, establishing foundations for that theory.
Thank you. Thank you very much for a very interesting lecture in historic point of view, of course. And my question is very simple, but if we can establish a year when the finite element method was born, for example, or we know that it was a process, but exactly when the first time was used the word the shape function, and the first time was calculated the beam or the bar or truss and yes, thank you very much.
So
thank you very much.
Right, so you know, it's a bit of religion. You ask that question to Professor Babushka, to Professor Oden, or to Professor Hughes, and you know, to the disease Professor Arjari, so before him Professor the founder in the States. I have a mental block right now. You'll get 5 different answers. No, Courant is you know, is usually brought out by mathematicians. Yes, 43, but they don't say that his methodology was, right, describing an appendix that he didn't consider even to be very important. Just a small appendix to the paper that was dealing with something else. However, it is true that in this appendix, for the first time, he used the term shape function, right? Later on, we begin to differentiate between the term shape function and the basis function. Shape functions used on the element level. Globally, when you glue them together, you obtain basis function. At least this is what I always emphasize. Clough, that was the name I was looking for. Clough was the first one that started to use the term finite element. Finite element. He specifically coined the term finite element, and he was behind the first application of the finite method to aerospace industry. The leadership was very quickly taken over by French. Mirage was the very first, you know, airplane that was designed with the finite elements. I just came from Norway, from Oslo, where I had a chance to talk with the great Professor Jacques Perriot, who led the French team about 40 plus years ago, right? That solved for the first time the transonic problem, discretization of the transonic problem, that is at the core of the design of the usual airplanes, right? Flying in this transonic regime. So, of course, huge credit goes to Professor Jaris, right, who died a number of years ago. Many say 10 years older than he really claimed to be. A great mathematician, a very strong personality. And of course, I should mention here Professor Olgierd Zienkiewicz, who died about 10 years ago or so, more than that, 2009, who was half Polish, half British, and who was, in many senses, a founder of finite element method and the whole finite element and computational mechanics community, computational engineering community worldwide. So his name popped out many, many times during the last week during the ACOMAS meeting. And I'm proud to have his medal with his name. I don't know whether you answer your question. So you will not get a single answer. You will get many answers. It's a bit a religious issue. It's the same thing who invented the first computers. You will get a different answer from Germans, British, right?
Okay, thank you very much. Next question.
I think they're tired.
Okay. So, Professor, let me say one more time, thank you very much. See you next time in Poznań.
Yeah, which means tomorrow. Thank you very much.
Hopefully we will not wait for you one more time 31 years. So, but you are here very often.
That
so
depends
yeah.
upon my colleagues.
Thank you very much.
Thank you. Thank you. Thank you.